Hello again, my dear students, and welcome to our second chapter with this grid connected photovoltaic course as a postgraduate course with the code RIN 616. In the previous section, we demonstrated together the technology process of a photovoltaic, starting from the basic material concepts, following to the p-n junction conventional silicon solar cell, and reaching some examples for new technologies, such as thin film technology and other perovskites and dust inside solar cell and organic solar cell technology. In this chapter, we will continue our bottom-up approach to scale up from the material and to the junction level to reach what we can call a device or a cell level. Today, we are going to make some sort of a demonstration related to a one cell demonstration, where in the next lecture or the next chapter, inshallah, we are going to scale up more and more to reach what's called a module level. So before going into the details of the cell, we have just to highlight, or let me say to flashback, some basic knowledge related to the electricity. One of these basic knowledge is the main difference between electrical power and electrical energy. A power, which is electrically defined in case of a DC as a multiplication of a voltage times the current, represents the power consumption instantaneously without the consideration of a time. However, in order to turn this power into a time, you have to use the term energy, which reflects the power according to a certain time period. So, for example, on one of the most famous example, if I go and buy this lamp with a power of 70 watts, knowing this information, if I told you, could you please estimate what will be my electricity bill by the end of the month? Of course, you will not be able to estimate the electricity bill, as I just gave you the power of the lamp. There is still a needed question or a needed information. How much time will I use this lamp per day or per month or whatever? So if I told you, okay, I will turn this lamp on for 10 hours per day, then you will tell me, okay, the energy consumed per day will be this 70 watts multiplied by 10, resulting what's called 700 watt hour per day, or 0.7 kilowatt hour per day. So this is a major difference, because whenever we consider a PV, we consider a PV in terms of watt. For example, I can tell you this PV module is 260 watt, 230 watt, or 255 watt, or 360 watt. However, when we start doing what we call the sizing process, we size energy, not wattage, because it's not the process of the PV wattage. It's a process of how energy this PV will produce per day, and I am as a customer, how amount of energy I consume per day. So in this same context, whenever we are considering energy, usually in our electricity environment, we will consider energy in terms of kilowatt hour or watt hour, not as we did in our previous mechanics or physics courses when we deal with energy in terms of joule. So usually our energy unit will be kilowatt hour. That's great. So let's now return to our PV, and let's focus on a PV module, which is, or a PV cell, which is an electronic device that converts the solar radiation into an electricity. Maybe in the previous chapter, we have demonstrated the physics beyond this process. Let's now consider this process as a macroscopic process. I mean, We are not going to investigate more about the solar cell technology, but we are dealing with as a black box that converts sun into electricity. Okay, so first of all of you know, and we already have revised this in the previous lecture, that light in general and solar spectrum as a part of light consists of a quanta of what's called photons. Each photon has a frequency mu, or we can call it also has a lambda, a wavelength lambda, where the frequency and the lambda are correlated with this constant c, which is, of course, you know, which is the speed of light. The energy of a photon can be calculated knowing the frequency using this h, which is a Planck's constant. Sun transmits us a big range of frequencies. However, our eye, as a sensor, can only detect this spectrum, what we call the visible spectrum, starting from 400 nanometer as wavelengths up to 700 or maybe 700 and something, reaching 800 nanometer. However, our sun transmits also some photons with energy greater than this blue spectrum, what we call the ultraviolet spectrum, and also it transmits another photons with energy lower than this red spectrum, what we call the infrared spectrum. We will consider this later on. Here we have to distinguish again between what's called radiance and what's called irradiation. The irradiance represents what we can call between brackets a power density. I name it with the word density because the unit here, as you can see, my dear students, is watt per meter square. So this is the amount of power reaching or transmitted from a light source per unit area per meter square. But if I would like to talk about this factor in terms of energy, I mean the energy density of my light source is then will be watt hour per meter square, and we would call it irradiation. So this is simply the difference between the term irradiance and the term irradiation. And as you can see, again, it's a time relation. Whenever you integrate the intensity or the irradiance, sorry, with respect to time, you will get radiation. For examples or some static numbers, the sun produces 380 times 10 power 21 kilowatt of irradiance, which reflects a total radiation of 3.2 times 10 power 27 kilowatt hour per year. However, Earth reaches 1.7 times 10 power 14 kilowatt, or in other words, 22,000 kilowatt hour per person, 2.3 kilowatt per person, our global use. This is some numbers related to sun. What about the sun spectrum? As I just told you, my dear students, the sun spectrum reflects an extended portion, including ultraviolet, visible, and infrared. Physically speaking, maybe this is somehow beyond the focus of the course, but physically speaking, the sun can be expressed as a black body radiation, where you can see here that in a black body, the temperature impacted the spectrum. The higher the temperature, the higher the peak shifted toward the ultraviolet. That's why you can see for our solar spectrum here, you see this yellow curve. Actually, this yellow curve represents that our peak here is somehow in the portion of yellow or orange, and this justifies why our eyes see the sun in this yellow or orange color, because simply the maximum intensity of photons are produced, or the peak of the spectrum is at the orange or the yellow spectrum. So this is the black body radiation, and this is the equation. Of course, this is, as I mentioned, beyond our scope in this course. This is just for your information. Okay, so this is our solar spectrum. However, this black body spectrum passes a long trip till it reach our our Earth. That's why this spectrum is transferred to this, to this, to this, and then to this. This is what we call the air mass condition. The air mass is the standard used to represent the spectra on the sun. And the number written beside this AM or air mass is simply related to the cosine of the angle of detection. So whenever you have an orthogonal detection in the atmosphere sorry, in the space, for example, I mean cosine 0 is equals to 1 because the angle here is orthogonal. This is what we call AM0. The AM0 simply represents the solar spectrum before reaching the Earth or in the space. That's why those people who are dealing with solar cells, for example, for space application, they are going to use the spectrum of AM0, which is again the spectrum of the sun in the space. However, in Earth, the most standard technique of measuring our sun is what's called the AM 1.5G, which represents a cosine or 1 over cosine theta. I'm sorry, not cosine theta, 1 over cosine theta here, which means an angle of around 44.2 degree, which represents the average angle of the sun across the Earth. That's why usually in our standards, you will hear the word AM 1.5G spectrum, which equivalent to 1 sun condition. This is, by the way, my dear students, is very, very important parameter in solar cells, because this 1 sun condition, which is equivalent to 1,000 kilowatt per meter square, represents what we can call the standardist condition in a solar cell. So maybe in the next chapter, inshallah, when we are going to discuss together a data sheet, a typical data sheet for a solar cell, and whenever you have an IV characteristics or an efficiency or an output power, any of these parameters are measured under what's called the 1 sun condition. This 1 sun conditions is equivalent to what's called the 100 watt per meter square. And in this context, we have what's called the equivalent sun hours. In other references, we call this the peak sun hours. Let's now try to understand this very important concept related to the equivalent sun hours or the peak sun hours, because this concept will be widely used in our PV sizing. Okay, so let's try to demonstrate the concept in a very easy manner. If you go to an electronics shop and you bought a PV module, let's say this PV module of 1 watt, a very simple module. So you have a PV module of 1 watt, and you fix this PV module in your roof somehow to be directed to the sun. And I told you, please, can you please tell me how much energy you are going to produce using this PV module? Simply, you will answer that you will not be able to calculate it. You already have a 1 watt, but you will tell me, okay, for example, sunrise at 6 a.m. morning, and sunset at 6 p.m. Evening or afternoon, and this will results are a difference of 12 hours. So this PV will be directed to sun for 12 hours each, and now the energy is power times time. So simply speaking, energy will be equals to 12 watt hour. So of course, my dear students, that this is wrong. Why this is wrong? Again, let's remember. This 1 watt is recorded or measured under what we can call the standard test condition. Assuming that sun is 1 sun of 100 watt per meter square or 1 kilowatt per meter square. But what will happen actually that whatever the country you are in, the solar radiation of the sun will take some shape of something like that. This time, and this is the radiance. So in early morning, the solar irradiance will be very weak. So it dries up till it reaches its maximum, maybe around noon time. And it will somehow stay keeping maximum for 1 hour to hour, whatever. And then it will reach its minimum. So when you multiply, my dear students, 12 by 1, you assume that the whole 12 hours are of 1 sun condition of 1000 watt per meter square, which is typically wrong because not all the time the sun will be in the 1 sun condition. For example, in the early morning by sunrise or in the late afternoon with sunset, the intensity of light or the intensity of the sun will definitely be very weak. So the correct answer will be something like that. Is that you should weight this 1 watt with respect to the intensity. What I mean is, if you assume that the maximum here is 1000 watt per meter square, this is the maximum, then during this period only, you can multiply, you can assume a 1 watt production, because here this is a one sun condition. For example, let's assume that this is from 12 to 2. So during this period only, during these 2 hours only, the sun can be assumed, or the production of the energy can be assumed of 1 watt times the period, which is 2 hours. So in this region, you will produce 2 watt hours because your production is 1 watt and you are at a standard test condition. So 1 watt is correct. And you multiply it by 2 hours. So it's 2 watt hours. However, in the extreme case of the curve, either here or there, you are not able to assume the 1 watt condition. You have to re-weight this 1 watt condition based on the sun intensity. For example, if the sun intensity is 1000 watt per meter square, or simply we can say this, if this is 1 sun, then the production of energy of power is 1 watt. If this turned to be 0.5 sun, then the corresponding wattage will be 0.5 watt, and so on. So what you are going to do is simply, you are going to say that the energy produced is the power multiplied by or integrated by time. And you will collect here the area under the curve so that you can assume that or calculate the overall energy. Please take care that this bell shape is function of the longitude and latitude, or in other words, is function of location across the earth. So it differs from one location to another. And also its function in the season. This curve in summer will be totally different with respect in autumn or in spring or in winter. That's mean to calculate the energy produced for this small 1 watts PV module, you have to have a big data set of information related to different locations and different days of the year, so that you can say, okay, today is the 1st of October. We are located in Cairo. Then simply we have to go to the data set, to our database, and get the curve of the 1st of October in Cairo, and then we can calculate the area under the curve to know the total energy. As you can see, it's a very sophisticated process to calculate the energy per day. Accordingly, people start to think about alternatives to make this process easy. We agree that our curve is something like that. So not all the time the power, the sun radiance is at maximum. It takes some sort of a bell shape. Okay, what if we calculate this area under the curve by any mathematical manner, and then we equivalent this area to a shape of a rectangle? So the area of the rectangle is somehow equals to the area of this bell-shaped curve. The total area under the curve here and there are equal. Now, what is this rectangle? We adjust the height of this rectangle to an intensity of 1 sun. And the width of this rectangle, which is of course a time axis, will represent what's called the equivalent sun hours. And as I mentioned to you later on, some references told it peak sun hours. So if I told you that in Egypt, in autumn, we are now in autumn. So in autumn in Egypt, the peak sun hours, or the equivalent sun hours, is 4.5 hours. The width of this rectangle is 4.5. And your PV module is 1 watt. That means that simply, if you fix this 1 watt PV module to the sun per day in autumn, it will produce 4.5 times 1, which is 4.5 watt hour per day. So you estimate the energy of this PV in just one step calculation by using this equivalent sun hour or peak sun hour model. Again, as I told you, this bell-shaped curve change per location, per season time, or per day across the year. Accordingly, this peak sun hour or estimated equivalent sun hour will change also per location, per across the year. In Egypt, for example, we say that our equivalent sun hours is varying from 4 to 5. In other words, from 4.5 to 5.5 across the year. Of course, you will find the minimum in winter and the maximum in summer, and what is in between reflects both spring and autumn. So in this case, you can make a very easy and rough estimation for your energy production of a PV module just by one click. For example, when you buy a PV module in Egypt of 100 watts, average of peak sun hours in Egypt is 5 hours, then the calculated or the estimated energy to be produced per day in Egypt will be 500 watt hour per day. In just one simple calculation, you make the estimation. And this is the added value of having what's called the peak sun hours in calculating the energy produced from a PV system. Okay, so this is the peak sun hours or the equivalent sun hours model in calculation. We already have highlighted the concept of commercial solar simulators. I think we already have highlighted this in our zero lecture. If you remember, when I talked somehow about our LED-based solar simulator, unfortunately, this is not a recorded lecture over YouTube for data confidentiality, but you can still read about our customized solar simulator by just going through my publications. I think you will find more than one publication considering these solar simulators, but simply speaking, solar simulators are those commercial or artificial lighting source that can be used to express or to produce, to generate a light spectrum, which is as much as equivalent to the solar spectrum. Of course, the higher the matching, the higher the qualifications or the quality of these solar simulators. Solar simulators are characterized based on three factors. Actually, what's called the temporal stability, or the stability of the light source against time, what's called the uniformity, which means within the area, targeted area, to what extent light is uniform, and what's called the spectral mismatching. So you can hear about what's called the AAA solar simulator. That means that this solar simulator is classified as an A class in terms of temporal stability, uniformity, as well as the mismatching with the solar spectrum, minimum mismatching, of course. And this is the solar simulator. Okay, so then the next will be, we already discussed this AM conditions with AM1 and AM0 and so on. This is what we have done. Okay, in the next part of this lecture, my dear students, we are going to consider a very important factor related to solar cells, which is the IV characteristics. What is an IV characteristics? How we can measure, what type of parameters we can calculate from the IV characteristics, and its importance with our calculations. Then we will turn to another important point related to what's called the small circuit model, or the equivalent model for a solar cell. So this will be done in the next part of our lecture. Thank you very much for your concentration, and see you later on in the next chapter.